Supplemental math videos from Circle Christian School.
SAT Exponents. Expect the unexpected and look at what could be. You really have to understand your concept to be able to manipulate it. There's no easy cure here, but to see it, try it, learn from it, and hope it works the next time. All right, let's take a look at your basic exponent rules. That if you have the same base times the same base, you'll remember that we add the powers. So when playing with manipulations, realize that a to the first power times a to any power is the same thing as a k plus 1. Another example would be a to the second power times a to the power of k is the same thing as a k plus 2. All we're doing here is allowing for a variable up in the power. Next one is if you have same base to a power over same base, then we're going to subtract the powers, top power from bottom power. And again, you can work with a little bit of manipulation here, that any base always has a power of 1, but it can have a power of 2. It's just a constant number. We're putting variables and constants into the power here. So just depending on the order will dictate how it turns out here with the subtraction. And any power being powered up, same thing, we get the power times the power, but those can be split up into several different ways also. So if you had a to the power 6, it could be a to the power 2 then powered to 3, same result, or you can see it as a to the power 3 powered up by the power 2. Still gives you a to the power 6. So we're kind of doing a bit of factoring inside here. All right, let's try an example here that if we have 3x minus 2y equals 5, what's the value of 8x over 4y? Couple ways to attack this at the same time. The first thing that we can do is see if we can make for some same bases. And we got an 8 and 4, so we try to see if there's not a base that they share, which would be 2. So using that last power rule that I went over, that would be 2 to the power 3, like so. And then we would power it up to the x. Gives us the same result as 8 to the power of x. But this gives us similar bases and allows us to work within the powers. So you can either start thinking of that from the first, or you can do it a little bit more toward the end here. Then, because we've got x's and y's, always think about substituting for one value here, one letter or the other, because then that allows you to be able to work in same variables, common terms here, like terms, and then you can do adding and subtracting and manipulation that way. So in class there, we actually tried doing it both ways at the Calvary campus and found that it really didn't matter if you solved for x or if you solved for y, you were still ending up with a very similar result. So here we just solved for the x, and we plugged it back in, and that allowed us to, when we changed the powers here, we had a 3, power of 3 here, and we're going to distribute that out, plus the 5 over 3. And then this is just the y. All right, now what that's going to allow us to do is, like I said, we're going to distribute this out, and then we can take the top power and then minus the bottom power. So that's going to give us a 2y plus a 5. It's kind of funny how this really works to get rid of that little denominator down there. Then minus the 2y, and then, okay, those are gone, and it's going to leave us with 2 to the 5th power, or 32. Now, will they be quite like this? Somewhat. It's knowing that there's this manipulation of powers that are happening, and you try to find something that is going to seem like a reasonable answer. In truth, if you really know what to do with the powers and manipulating the powers, you could really do it in about 30 seconds and find your answer. I know that sounds like it's very daunting. Don't let it be. We're just practicing, seeing things, and trying to match it up and learn from it. Okay, the problem we hate, which I really still don't have an answer to, and just going to put it in here. And when I find the answer to it, then I'll be able to revise the audio. But if 3 to the power of k plus 1 minus 3 to the power of k equals m, what is 3k plus 2 in terms of m? So first thing we have to ask is, what does it mean in terms of m? So anytime you see terms of m, it means we want that letter into the variable term. So we have to manipulate things back and forth till we get some term that has m in it. So we're going to have to start to find ways to get 3 to the power of k. It's just kind of the focal exponent that's working here. But remembering that we can split up our exponents here, that 3 to the first power times 3k equals 3k plus 1. And although we played a little bit to get this 9 here, I was wrong in that and realized what was wrong with the 9k bit, that you have to follow the order of operations, which is what's bothering me about the next step here, is the order of operations. That order of operations says you have to do the powers first before multiplying. So I cannot take the 3, which is a power of 1, and multiply it to the 3 with the power of k, because I need to know what k is first. I have to do that exponent thing. Therefore, leaving us with a power that has unlike terms in it. That's where the k plus 1 comes from. So taking it back to what they had in the book, they split it up so that you had the 3 times the 3 to the power of k minus power of k, 3 power of k equals the m. Now here's my problem. I still haven't really figured out where the 2 came from and what happened to the negative 3k. However, just on a sidebar over here, we did play a little bit with it just to see if some substitution things worked, all the way up to even just seeing if the answer made true statements, which it did. We just don't know where the 2 and the negative 3 come from. But if I take 3 times 3k minus 3k here and check to see if it equals 2 times 3k, and we let k equal 2, then we have, following our exponent rules, we have to do exponents first, our order of operations, then we have to do any multiplication and then any subtraction. So I get 3 times 9, which is 27. Take away the 9 is 18, and checking to see if 2 times 9, yeah, it's 18. I also tried this with the power of 3 and 4, and it did make true statements. So therefore, 3 times 3 to the power of k minus 3 to the power of k does equal 2 times 3 to the power of k. Well, in the manipulation, then that's where we get, we divide out the 2, and that gives us m over 2. And we want a 3k because that's what is sitting up there with the 3k plus 2. So that's why we need the 3 to the power k. I'm going to split that off just like I did the other one. It gives me 3 power k times 3 to the power 2. I'm going to use substitution because I now know what 3 to the power of k is, and substitute the m over 2 and times that to the 3 squared here, and that gives us the 9 over 2m. So let's try the one that is in the exercises here for your practice. If 5 equals a to the power of x, then 5 over a equals, okay, that there's really kind of a couple of ways to play with this. I hate to say that. In class, we took a look at what was happening with our answers here so that we could see them, and we saw that this one was ax times a to the power 1. This was ax over a to the power 1. The next one was a1 over ax. And the last one is as it is. And if you wanted to, you could see it as ax over 5. Both of those mean the same thing. Well, we can almost discount that one because there's no power thing going on, and we had a power somewhere somehow to begin with. So now I need some sort of manipulation that's going to wind up with that power thing. I can almost count this one out too, just because of the one being on top. So I'm going to look at the other two here. And if 5 equals ax, see, this would equal ax over here, because that's what it says. And it's going to be some sort of fraction kind of thing. And I need to have a common denominator for it to be true here, kind of thing. So a would obviously just equal the a, because then it would make for a true statement. And here we see it leads us with the answer of B. All right, let's take a look at number 21. This is a classic expand then condense, but you got to remember that when you got the variable in there that you can actually split these little guys up. So I've taken the numerator, the top here, and taken the 2n plus 1 and split it up, power of 3, and then expanded it out just so it's a little bit easier to see. So, you know, b to the power of 2n times b 3 times there. Took the bottom one, expanded it out also using the rules that we had. And now I'm just going to get rid of things. We have a b here, a b here. We have 5n here, so I am looking for 5 here also, so I need 5 of them. So there's 2, there's 4, and that leaves me with 1 there. Okay, so that's gone. And then we have a bn over a bn, so those are gone. And that leaves me with a b and a b, and that equals a b squared. Expand and condense. The big thing here is to realize that you've learned kind of a new little calculus rule here of being able to actually split up these bases that have a variable inside the power by using your power rules. Don't be afraid of them. It's about manipulation. The more you can manipulate now, the better it is to see later. All right, kiddos. Have a great day.